Hi, I'm Katherine Schwab, an assistant managing editor here at Forbes covering technology. And I'm stoked to be here today with Nick Harris. He is the CEO of Lightmatter, which is building AI chip tech that is relying on light rather than electrical signals, which is how chips typically work. So, Nick, thanks for joining me.
Yeah, happy to be here. Excited to tell the story.
Yeah, so let's just start by talking about why light. What advantages do you have if you're trying to use light to send information versus traditional electrical signals?
Yeah, I think that gets into a little bit of the origin story for how the company got started. Um, Basically, if you look at how computers have scaled, how they've gotten better, faster, more efficient, cheaper, more ubiquitous over the past, 50 plus years, it's come from these concepts of Moore's law and Dennard scaling. Transistors would get smaller and more efficient every 18 months, about twice for both of those quantities. That broke down in maybe 2005. And so around that time, people started to lift their heads up and look around and try to find new sets of physics that might be able to augment how computers work and continue to drive scaling in cost, energy efficiency, and speed. Now, there are a lot of choices. People have looked at things like carbon nanotubes. They've looked at different materials for the transistor, which is the switch that's used in computing. But one of the areas was light. And that's what I work on at Lightmatter. And I worked on at MIT during my doctorate and postdoc there with my co-founder. And the reason light's interesting is that it has a fundamentally different set of physics associated with it when you compare it to like transistors running on electrical signals. First of all, if you think about the way the world is wired, the continents are connected using light. So the internet's running over optical fibers that are in the ocean. Cities are connected together using light. So there's optical fibers buried in the ground, and that's carrying the data. So what's special about the light? Well, it turns out you can't send signals across really vast distances using electrical signals because they just kind of dissipate. The signal dies and it just goes away. With light, you're able to transport data over extreme distances. And not only that, you're able to send data at very high rates. One of the things that we just did is we announced an 800 gigabit per second optical fiber. Just to put that in perspective, your house has 1 gigabit per second internet connection. Each one of our optical fibers can power 800 houses. So light is pretty incredible when it comes to transmitting information. And that's some of the special properties, and we can talk about what we do at Lightmatter and the context and all that too.
Yeah, no, for sure. So I guess before we get into more of the nitty gritty details here, can you help us understand why does this matter right now in this moment? Like, what are the pressures on compute right now, given the AI boom that's happening, that makes this approach really interesting for this moment?
Yeah. When you look at computing in general, it's always felt like a breakneck pace. People have had to release new fabrication technologies. Think about TSMC with N7, N5, N3. There's this relentless train of progress for technology, specifically the fundamentals of technology, like the computing elements. Now, that rate was really fast. The cadence was about 18 months. With AI, that 18-month improvement cadence was reduced to about 3.5 months. So you're looking for doublings in performance and cost every 3.5 months. When that kicked off, you had to switch to new technologies. Typically, the semiconductor industry, which is the field that we work in, is very resistant to change. They want to squeeze every drop they can out of what they have before they make any giant leaps to new technology. When you ask for a 5x improvement in the rate of progress, something new had to come. And that's why light, the moment is here.
So tell me a little bit more about the breakthrough that you announced earlier this year in terms of that fiber cable and the 8x improvement.
Yeah, so at Lightmatter, we build photonic chips that link together GPUs and switches to build these giant AI supercomputers. There are a couple things that you want to get right when you're building out these connections between these GPUs if you want to build a million GPU supercomputer. One of them is you need a lot of efficient utilization of each piece of glass, each optical fiber that you're connecting to a chip. The other one is you want lots of connections to the chip and lots of bandwidth, hundreds of terabits per second. of bandwidth. And just to put that in context, your house is 1 gigabit. A terabit is 1,000 gigabit. So I'm saying 100,000 houses worth of bandwidth or beyond. So what we announced earlier this year was a technology where two chips could communicate using a single optical fiber, sending 16 colors of light, 8 in each direction. So 8 are going from one side to the other, and 8 are coming back. And so both chips are talking with a single piece of glass, a single optical fiber. And then we scaled that with our M1000 platform to have 1,024 lanes of this. So that chip is running at 114 terabit per second. So 114,000 houses worth of bandwidth. It's like a city.
I appreciate the houses comparison because for us non-technical people, it's hard to wrap your mind around the scale and the complexity that we're talking about. But at the core, these are really like the engines that are building the AI models that people are using every day. So there is this huge demand for more and more and more compute. What have you seen in terms of demand for this product since you launched it?
Well, earlier this year, NVIDIA announced that they were working on optical technologies to connect to their GPUs. They're trying to increase the size of the domain in which GPUs can communicate at high speed. We've been working on this problem long before NVIDIA started getting into the game, but we're really happy to see them announce that they're doing it. And the reason is the entire ecosystem now knows that it's time to switch to photonics. The level of interest is excitingly exhausting, I would say. Tons of customers, lots of demos. And we've had the opportunity to really showcase our hardware in public settings. And I think people are just incredibly excited about the tech now. And 8.5 years in, it's time.
Yeah, I mean, that's a long time for you to be working on bringing this to market. Will you talk to me a little bit about those early years? When did you, what convinced you to start a company when you were still working on this in an academic setting?
So I'll go a little bit earlier than that. So I was an R&D engineer at Micron in 2009, and I was working on transistors and the device physics, like how do you scale the transistors? How do you make them better? And what I saw at the time was that the roadmap for making transistors better was kind of at the end. I talked about Moore's law and Dennard scaling. I could see that was kind of over. And so I went to graduate school at MIT to figure out how to augment computers. Maybe you can't replace everything about the computer with light, but what pieces might you be able to replace that could drive efficiency, drive speed, drive costs down? And so that's kind of what I worked on at MIT. And while I was there, the deep learning revolution kind of kicked off. And you could feel it. This was 2015 was when you could really start to feel it. Everybody at the school was kind of looking at how they could leverage this deep learning to control systems that were so complicated that they were kind of incomprehensible to people. And so we were learning to build these AI models. And at the same time, I was building optical computers for quantum computing in the lab. And I saw that those machines that I was building using silicon photonics, which is a technology that you build in standard electronics fabs, but that uses light to transmit information, I saw that that could actually be used to accelerate AI, both in how chips communicate, but also potentially how they do calculations themselves. And so I think a lot of things aligned when we were starting the company. We saw the end of scaling for transistors. We saw the AI boom start to happen. And we saw that the commercial foundries that could, think about companies like TSMC, Global Foundries, and Tower, commercial companies that build the wafers that run the world's electronics supply chain, they all started to look at building silicon photonics. So we had the convergence of those three things, and that was the kind of fertile ground that we came from.
But it's taken quite a while to get here. What were some of those early challenges? I mean, did investors buy it right away?
So at least in our story, I'll tell you how we experienced it. We went to this MIT competition called the 100K, which is MIT's top entrepreneurship competition. If you win, you get $100,000 to start your enterprise. We did that. We won the 100,000 there. We went to Harvard and won this President's Challenge. And they had like 75,000 or something like this. And after that, I think investors knew that we were onto something. At least the way we were telling the story and the opportunity was fundamentally true. And so investors really wanted to come in and back the company at that early stage. When you think about the challenges that we've run into, well, we've had to invent a lot of how all of this technology works. From the lasers to the way that you control the devices to robust manufacturing techniques, we've had to innovate across all of these fronts. It's been a very long journey to get here, a very deep technology stack, and we've built quite a moat around us.
So when it comes to efficiency, because that seems like one of the core things you're offering here is more efficient data centers. What are the challenges that data centers are facing right now? I mean, we've seen folks like Elon Musk build massive supercomputers extremely quickly. Like, there is so much building happening in this space. What are those core blockers for efficiency right now, and why do you see what you're doing as a solution? And how do you then convince these massive companies to take a bet on this new technology?
Today, the rate of growth in the amount of AI hardware that's deployed is just crazy. In Texas, right now, there's 27 gigawatts of AI compute coming online. Texas, as a state, consumes about 100 gigawatts of power. So a third of the power of one of the biggest states in the United States is going to powering these models. So you think about that. There are a lot of fundamental pieces of the infrastructure that are going to be constrained from a supply chain perspective. Transformers, just generating the power. People are looking at nuclear reactors to try to power this stuff. Man, wouldn't it be nice if you could squeeze a lot more compute out of those data centers? With what we're doing, we can take a 1 gigawatt data center and make it feel like a 4 gigawatt data center from a performance perspective. Think about taking a foundation model from Google or name any of the frontier model labs and releasing that 3 times faster. So instead of every 6 months you get a new model, how about every 2 months? Think about the impact that has on the AI race and the compound acceleration of training models and intelligence in general. So that's what we can do. And the way that we do it in particular is by allowing these very fast groups of GPUs in these domains where they can talk quickly to get even bigger. Right now, you can only get about 72 GPUs to talk at high speed. As soon as your workload is bigger than that group of 72 GPUs, you notice a huge drop off in performance. And so what AI scientists do is they map the problem onto groups of 72 GPUs. They don't want to do that. That's not the goal. They would like to have 1,000 GPUs or more that are all talking at very, very high speed. They really feel in these high bandwidth domains, it all feels like one giant chip. But as soon as you spill out, it feels like a giant drop off in performance. And so what we're doing is we're enabling the size of, that's called a scale-up domain, to get very large. 10,000, 100,000, a million chips that are all talking with incredibly high speed and driving that time to train and that 1 gigawatt to feel like 4 gigawatts of compute. So how about that 27 gigawatts actually looks like 100?
Well, okay, there's a lot to talk about off of what you just said, but one obviously is energy. I mean, that's a colossal amount of energy. It's mind-blowing, and the US grid is just not going to have enough energy at the pace that we are growing. There's really going to be a major shortfall here. So it sounds like what you're building could really help with that energy efficiency problem.
Absolutely, it could. And I hope that we can build fast enough to not have a shortfall happen. I haven't looked at the numbers super closely myself, but I think there's a chance that you can lay the tracks and keep the powertrain going, keep that growth rate going. But energy production is an important piece of the puzzle now, especially in this AI era. And you think about 27 gigawatts, a quarter of Texas. How long until we're at the United States power consumption? Probably not very long. So there's going to need to be a lot of innovation in that front. And the more efficiency you can squeeze out of every GPU, TPU, XPU, the better.
So what the 72 cap, I didn't know that. I think that's really, really interesting. And yeah, it's like mind blowing to think about if the systems that have been built now were made with these constraints that you're describing, like what could be built if those constraints weren't there. I'm curious. I know this isn't your area of expertise per se, but I'm curious, like, what kinds of systems could be built when you have so much more ability to compute.
Yeah, so here's a couple of things that you could do. With our photonic networking technology, by the way, our chips are called Passage. We also build lasers that power them called Guide. With that technology, you could build much bigger frontier AI models, very, very large, 100 trillion parameter and beyond. And the reason is that you can lace together thousands of GPUs. Each GPU has a certain amount of memory, but you're multiplying that memory across the number of GPUs. So the more of them you have talking in an ultra high bandwidth domain, the bigger the AI model you can serve at a high speed. So imagine, Gemini 9, something like that. That's what you can enable with the technology and beyond. And then if you look at, there's a new field, which is reasoning models and deep research. I think a lot of people are using deep research, and I think multiple companies have named it the same thing. That kind of model is spinning up a ton of GPUs, and they're all running work in parallel. And you can actually accelerate the time to answer. Right now, sometimes you kick off a deep research program and it takes 10, 12 minutes to give you an answer. How about 1 second? How about instantaneous? So that's what's possible. I think we can massively increase the frontier performance, bigger parameter counts, which means more intelligence, and we can also speed up that interaction so you can do really advanced things really quickly.
What, in your mind, would be like the holy grail of photonics in terms of a data center that was built kind of from the ground up using this technology at every layer? What would that look like?
Today, these data centers look like a bunch of mini brains that are all computing in parallel. You ask a copy of the question to all of these mini brains. They're all 72 GPUs computing. What if you had 1 million GPUs that all acted like a single giant brain? That's kind of the dream that we're looking at. And 1 million's just the beginning. We'll be at 1 million very soon. I like to think about the scale of this power consumption growing. It's just doubling at an obscene rate. There's going to be 10 million, 100 million, billion GPU data centers, and that can all be linked using photonics, acting as a single computer. Imagine what that AI model will behave like and what it'll be capable of.
Yeah, it's a little scary if I'm honest. It's like pretty scary to think about. I mean, a bunch of companies are racing to develop like superhuman intelligence or intelligence that like actually could mimic a human brain. But it certainly feels like we're pretty far away from that. And it sounds like we need these kinds of hardware improvements to be able to get to the kind of scale that you're talking about. Though the way you reacted, I'm thinking maybe you disagree with me about how far away this stuff is.
I mean, I'd say we're using AI everywhere at Lightmatter, and I could only dream of having the tools that we have now when I was in graduate school and researching the stuff that would become Lightmatter. Man, it's an incredible efficiency booster. I think these are very powerful tools.
Yeah. Okay. I have to ask because it's a question everyone is talking about right now. Is this a bubble? Is the kind of big infrastructure build out, which is kind of the signal, along with the sky high stock market prices, from your vantage point, are we in a bubble right now?
From my vantage point, I see no slowing in demand or interest in next-gen technologies or build-outs at all. I think there's a lot of talk in the press about some of the commitments on data center build-outs and how those will be funded. I think that they'll find a way to get that stuff funded. Fundamentally, the technology is delivering what they thought it would deliver. And that's crazy because this has been going on since 2017 when Google invented the transformer. And the whole world basically made a bet that these AI models would keep getting better at this incredible rate. One of the possible things that could have happened is it could have slowed down. We could have had this incredible trajectory that just kind of tapered off. It's not tapering off. It just keeps getting better. So that's profoundly interesting. And I think that will drive huge economic value. And it is. So I don't think it's a bubble. I'm very shocked pleasantly at how well these models keep scaling.
Interesting. Though there also has been, a lot of talk as people do start to talk about the limitations of LLMs and the transformer architecture and think about, for instance, moving around in the physical world, we don't have nearly as much data to help AI models like have spatial reasoning, things like that. So I think we've got a ways to go in terms of making something that's like truly artificially intelligent.
Yeah, I mean, I think robotics is an exciting field, and watching all these startups, including Tesla, which is not a startup, building these machines, and the rate of progress there also seems very high. So generally, things are looking very futuristic and exciting to me.
I'm curious for you and your company in this moment, what is your moonshot vision for Lightmatter?
Yeah, moonshot vision for Lightmatter. So I think ultimately we're on this trajectory where we're trying to replace some of the core components of computers. Right now, it's about how they communicate, and we're going to replace how that's done today, which is with electrical wires, with light. And that's the journey we're on now. We're also working to create new sources of light that are incredibly bright and that power crazy amounts of bandwidth. Think about a petabit per second, which is 1,000 terabits. It's 1,000,000 houses worth of bandwidth. Okay. So on that
Okay.
journey,
I do need that
houses.
house metaphor, so I appreciate it.
Yeah, absolutely. So I see us getting to a point where computers are no longer constrained by their ability to communicate with each other and their ability to access memory. And at that point, I think that there'll be a need for a fundamentally new type of computer, the calculations that underlie it. Earlier this year, we published a paper in Nature where we showed that you could actually run state-of-the-art AI models on a computer that was using light to do calculations rather than using electrical signals to do calculations. Now, I think this is 10 plus years away, but I see this incredible journey at Lightmatter towards making fundamental improvements in computers and driving that rate of progress. I do have a crazy prediction, which I think will end up being true. I think that Mars will end up being a data center. And I think
Whoa.
it's because, right?
Okay, say more, please.
Yes, you're already hearing people talking about, even Google, talking about building data centers in space. Eventually, you can imagine shipping huge numbers of these XPUs, these GPUs, TPUs, to a planet like Mars and covering the surface with these billion GPU supercomputers. We're going to keep scaling the amount of power we're using. We're going to keep scaling the amount of land. You're going to want to pick a spot that's not like a national park to put that computer. And you think about SpaceX and what they're doing, they're building towards a future where that's possible. So I think the future is very exciting, and there's a lot of elements of sci-fi that are probably going to come true.
Wow. Mars is a data center. That's very like Death Star vibes. And also, I feel like Elon wants to go live on Mars, not cover it with a data center. So there might be some conflicting incentives there, shall we say?
Yeah, I don't know if I'd want to live on Mars. I don't know if that would be very. It's not that, it's orange. That's
It's not very,
nice.
yeah. It's not doesn't seem like that nice of a place to live. Maybe he'd just rather visit and then create his own empire there, his computer empire, robots and data centers. Nick, thank you so much. This has been so interesting. What a fun, very sci-fi note to end on. Thank you so much for joining me.
Absolutely.